Welcome back to the alcohol chapter where we look at reactions of alcohols, preparation of alcohols. We're still in the preparation part, and we today are going to be looking at preparation of alcohols by ketone reduction. Remember that ketones are just C double bond O, and then coming off of that carbonyl carbon, as we say, there's two R groups. Could be the same, could be different. That's just carbon groups. Okay, so we know that the oxidation state of a ketone for that carbonyl carbon, meaning that carbon bonded to that oxygen, is going to be +2. And if you forget how to assign oxidation states to organic molecules, just remember that split the bonds ionically, and whoever wins gets the negative, whoever loses gets the positive. So if we look at assigning oxidation states here, we carbon-carbon, that's really a tie. There's no electronegativity difference there. So carbon-carbon, no one wins. It's +0 for each, right? So right now that carbonyl carbon is at oxidation state 0. But when we look at the oxygen bond, if we were to look at the electronegativity difference between those two, the oxygen would win. And it would win every single time because it's more electronegative. So it's going to get a -2, but the carbonyl carbon is going to get a +2. And when we add up, we take the sum of all of those little wars, you could call it, little battles. That carbonyl carbon has an oxidation state of +2. So what we mean by ketone reduction is turn that carbonyl carbon's oxidation state from, let's say, +2 from when it's in a ketone to anything less, +1, 0, negative even. And we can do this, and what we're going to see in this organic chemistry lecture is turning it into an alcohol. And that would actually give it an oxidation state of 0. Let's just see why that is. So we have our ketone here. We give it a nice reducing agent, and that's going to bring it down to this molecule where we add a hydrogen and we add an alcohol here, right? So our specific reducing agent did this here, and we'll see what those reagents are in just a moment. Maybe you can guess. Put it down in the comments, why don't you? So carbon-carbon, remember, there's no real winner there when we ionically split the bond, hypothetically, to assign our oxidation states, so it's just 0. Carbon-hydrogen, carbon's about 2.5 Paulings, hydrogen's about 2.1. Carbon is slightly more electronegative, and therefore it's going to get -1. So we're at -1, we're doing great, we're already reduced. But sadly, we have that OH group, and we know that oxygen is more electronegative than carbon, so it's going to steal. It's gonna be the winner of that. It's gonna get -1. Carbon gets +1. You add it up. Hydrogen gives you -1. Oxygen gives you +1. Cancels out. You get 0. The carbon groups add 0. So this molecule here is 0. So we went from +2 on that carbonyl carbon to 0. Now I want to get into the mechanism, see the reagents that we're going to be using in these reductions. Okay, so if I asked you to make an alcohol from a ketone, you might actually think of this reaction here. So if I have my beautiful little happy little ketone, it kind of looks like a dude that's running in a nice little field, so we'll draw him some grass to run around in. He's jumping in the grass, as we say. Anyways, so we have our ketone here, and you would think, if you remember, catalytic hydrogenation, a double bond. If we used, what would hydrogen gas's color be? I think it would be like a nice navy blue. It's hydrogen gas. And if we use like let's say a platinum catalyst, so PT, platinum. So we remember with alkenes, if we were to do this reaction, hydrogen and that double bond, carbon double bond, it would kind of react with that platinum surface, kind of bond. And then that hydrogen would come in and bond to that surface, and then there would be some transfer, and we would get like if this was ethene, this would be ethane as our product. So that's what we would get. Here you can do the same, but there's a problem. Your reaction conditions need to either be extremely high temperatures or extremely high pressures. So you need this or really high pressures to have this reaction occur. But what you would see is you would get an alcohol. And that's exactly what we want. But these conditions are annoying in the lab, right? Hydrogen gas, getting that without oxygen is kind of hard. Platinum can be kind of expensive. And getting those higher temperatures and pressures can be kind of annoying. So we can do this another way. 2 ways, actually. I'll show you one to start. and I'll draw the other one down here. We're going to use a reagent called sodium. We kind of saw this in the last video, borohydrate. And our second reagent that will do about the exact same thing, there are some differences, is lithium aluminum hydrate. So when we look at what these look like, just a generic thing, we're going to have our cation, and we're going to have our anion, which is going to be some metal, which I'll call M, and then hydrogens, and it will give that metal negative charge. And yes, I know boron isn't a metal, but besides the point. So we have that atom in the middle, negatively charged cation, positive charge, and we have those hydrogens. So we have to use one of those reagents for this reaction. We'll see the difference. With sodium borohydrate, you want to use a protic solvent, so you could use methanol, or if you don't like methanol poisoning, you could go with water. Water's a good one. All right, and for lithium aluminum hydrate, you want to use a protic solvent that is, or not a protic solvent, an acid, so you would want to use like H2SO4, and that would be good, right? So any real acid, you need to use acidic conditions. Alrighty, so let's get into the reaction here. If we were to do this reaction, we'd get this compound. And you'll get the exact same thing for the lithium aluminum hydride. Now, there is an important thing here to note, is that you need to do these in separate steps for the lithium aluminum hydride. A lithium aluminum hydrate is a lot more reactive than sodium borohydride, right? So because of that, this needs to be step 1, and this needs to be step 2. And you can explain that through electronegativity difference. I know boron is about 2.0, right? And this one, I forget, but the electronegativity is even crazier than that. The electronegativity difference between aluminum and hydrogen. So that allows for more polarizing bonds. Those hydrogens are more nucleophilic, as we would say. I want to get into the mechanism here now. So we'll start with our sodium borohydrate, or hydride, I should say. We're going to omit the spectator ion here. It's not as important for your understanding. It's basically just there to be an ionic species. So here's our borohydride. And our first step here is going to look a little weird, but once you get it, you're going to have it down. It's pretty easy. You'll see it a million times in organic chemistry. So if we have a negative charge here, we can neutralize it by just deleting one of these hydrogens, right? Boron naturally will have an unfilled octet wanting to make 3 bonds. So this bond comes out here and puts the hydrogen on that carbonyl carbon, and we're going to have a negative charge be brought up onto that oxygen. And we're going to get a compound as such. And just to make things ultra clear, I'll draw in the hydrogen here in red. So we have that hydrogen in red, and we have that oxygen there. We can't just arrow push an alkene group or a hydrogen off, so we need to protonate it. And we can do that with our solvent. So if we use something like methanol, so Me standing for CH3, and then we have our alcohol group. Quite simple. Oxygen just reaches out and protonates itself, and methanol becomes an alkoxide. And we're going to get our alcohol product. So that's reduction with sodium borohydride. Now we have lithium aluminum hydride. Remember, that aluminum hydride, as I said earlier, is much, much, much more reactive than sodium borohydride. We can even make, side note, we can even make this more unreactive by adding a cyano group, for example. We'll see that when we get to the amines chapter. Okay, so with lithium aluminum hydride with ketone, the first step here is we have our aluminum hydride, right? It's the exact same kind of structure as the boron one, although it's just aluminum, it's more reactive. What will happen first is we're going to do the same step where we go like this, right? And we're going to push electrons up to here. And we'll draw our hydrogen in green. And I will show you this here. So this needs to be done in separate steps. If you're in the lab, you'd have to get rid of all of your aluminum hydride or isolate this, but I assume that would be kind of difficult. Maybe get it in a salt form. But your next step here is going to be an acid workup. Now, you're going to see this a lot now that you're kind of familiar. Whenever you have a negative charge and you want to reduce it, one of the best ways you can do that is to protonate it, especially if it's oxygen. So here we're going to use a strong acid. We have H2SO4, but just to make things simple, I'm just going to go with H3O+, and that's going to take a proton off of that and give it to that, and we will see we will get the same outcome here of a secondary alcohol. So it's the same kind of thing, it's just how reactive do you want it to be. And later down on the road we'll see some key differences in reactions using one or the other. So that's going to be okay. Just a little side note here that I wanted to point out. Sodium borohydride, so we'll just draw that out here. Sodium borohydride, and that has a negative charge on it. And aluminum. Aluminum is kind of like, when I think of aluminum, I think of like an aggressive color. So we're going to go aluminum as red. But aluminum here and borohydride and aluminum hydride, we refer to these as delivery agents. They deliver a species of something to another molecule in some sort of organized reaction. We'll see a little bit down the road, we'll have the Grignard reagents. That looks something like this, right? Just a little sneak peek here. This is a Grignard right here. That's going to deliver a methyl group to ketones. So we'll see how that works later on in the chapters here. But remember that we call these delivery agents. So if you ever are like reading a paper or something and you see the word delivery agent, it's species, and for example these that will deliver something. So that hydrogen or that hydrogen there. So just an important note to add there. That's going to be it for ketone reduction. Quite a simple thing if you can get the hang of it really well. It's one of my most favorite reactions. Grignard's my favorite reaction. This is actually my most favorite chapter. It's easy. It's really fun. There's a lot of cool new stuff that you learn, especially with organometallics, right? Those are always really fun to learn about. But I hope that you guys are enjoying this series here. Sorry if the videos are a little long. I am quite a yapper, so I apologize. But I hope you guys have a wonderful day, wonderful evening, wonderful night, and stay awesome.